Okay, right. Just hello everyone. Sorry about that. A little bit of an issue there, kind of like setting that up. So I thought that on this particular live stream that what I would do is I would go through some integration questions, because I know that they're always like a really popular one. And I'm going to go through quite a few different kinds of ones. So let's have a look at what we're going to do. I'm going to go through, first of all, how to integrate. Let's do how to integrate cos squared. So we'll start off with that, just to start off with, integrating cos squared. So if you have any questions as I go through it, if you can put those questions in the comments, I should be able to see them. So I'm going to start off with cos squared, and I thought it'd be fun to do cos squared, cos cubed, cos to the fourth, cos to the fifth, and should you ever need it, cos to the sixth, just to show you how you would deal with those. And then once we've done that, I'm going to look at these two more complicated examples of how we would use like the reverse chain rule, okay, from this question here on the screen on the left-hand side as well, okay, over here. But first of all, let's deal with this one, a nice straightforward one, cos squared, okay. Now, the thing is, you can't use the chain rule backwards to integrate cos squared, because a rule of thumb is you can only use the chain rule backwards on something that could conceivably have come from the chain rule in the first place, okay. And cos squared could not have come from the chain rule because we haven't got any like derivative of the inner function. So what we need to do, and this is one that I think people are perhaps the most familiar with, we need to basically use an identity to change it into something that can be integrated. And the identity that we use is from the formula booklet here, cos 2x. So if I write down cos of 2x, cos of 2x is going to be cos squared minus sine squared. So cos squared x minus sine squared x, like that. And then because we're integrating cos squared, we want to change this sine squared into 1 minus cos squared. So we change that into 1 minus cos squared, like that. So we've now got cos squared x minus 1 minus cos squared, which goes to 2 lots of cos squared x minus 1. Okay, so that is equal to cos 2x. So we rearrange this in order to make cos squared the subject. So when we rearrange that, that's going to give us cos squared x is equal to a half plus a half cos 2x. Okay, so that's the first step. What we've done is we've taken an identity that we essentially can derive from the formula booklet straight away, and then we've changed it into cos squared is a half plus a half cos 2x. Now, the reason why this is advantageous is because a half plus a half cos 2x can be integrated really nicely. So we're changing cos squared into 1 half plus 1 half cos 2x, okay? And as I say, please do ask me in the chat if you have any questions as we go through it. So first of all, a half is going to integrate into x over 2. And we're going to use the chain rule backwards on this one. So cos is going to integrate into sine. And then we need to divide by the derivative of the inner function, okay? And then add c. So if we're going to integrate cos squared, it ends up as being x over 2 plus a quarter sine 2x, okay? So that's the first one, nice and straightforward one. Now, the exam board, I think, pretty much know, the exam boards know that most people are confident with knowing how to integrate something like that. So I have seen them do it where they, and I remember this as an exam question not long ago. Let's say instead of that, they wanted to get you to integrate cos cubed, okay? Cos cubed x dx. Now this one's a little bit tricky because we've got a like slightly different thing here with the cos cubed. The trick, and as I say, I've seen this as an exam question. The trick for integrating cos cubed, again, we can't use the chain rule backwards on this because we can only use the chain rule backwards on something that could conceivably have come from the chain rule in the first place, okay? So what we need to do here is we're going to think of it as cos squared x times by cos x. So we reimagine cos cubed as being cos squared times cos. And then what we do is we change the cos squared into 1 minus sine squared, like that. Okay, so we basically change it like that. So we're going to have that cos cubed goes to cos squared times cos, which goes to 1 minus sine squared. Then we expand that bracket, so that gives us cos x minus sine squared x cos x, okay? And that's what we've got to integrate now. And this is really nice because cos squared is just going to integrate into sine. So cos integrates into sine. So no problem there. And now we've got to think about how we're going to integrate sine squared x cos x. Now, I know teachers have loads of different ways of like explaining how to do this. But I've got my preferred method that I like is when I'm trying to use the chain rule backwards, I try and look for something that is the outer function, the inner function, and the derivative. Okay. So in this expression here, my outer function would be something squared. Okay, so I'm going to write down something squared. My inner function in this case would be sine x. And the derivative of my inner function would be cos. So I look for outer, inner, and derivative. And then when we're using the chain rule backwards, what we're going to do is we're going to integrate the outer function and we're going to divide by the derivative of the inner function. Okay, so the something squared is going to go to something cubed, and we're going to divide by 3. So that means we're going to go to sine x all cubed because we've raised the power by 1 and divided by the new power. We've still got the cos x here, but now we divide by the derivative of the inner function. Okay, so when you integrate sine squared x cos x, it goes to 1/3 sine x all cubed. And you can check that by redifferentiating it using the chain rule. Okay, so that's going to go to there minus 1/3 sine x all cubed, add c. Okay, perfect. All right, so that is our integrating of, so far, we've looked at cos squared and we've looked at cos cubed. Okay, now I would just mention, let's imagine you wanted to integrate sine squared and sine cubed. Just for, I won't do the whole thing, but I'll just tell you what you would do. So if you have to integrate sine squared x dx, you do the exact same process. You basically go back to the double angle formulae for cos, but this time, instead of changing the sine squared for 1 minus cos, this time you would change the cos squared for 1 minus sine. And then just as we did before, you would rearrange it to make that cos 2x a subject. Okay. Now, when you do that, that's going to give you that sine squared x can be thought of as a half minus a half cos 2x. So you can see it's very, very similar to what we had before. The only thing that's happened is that whereas we had a plus before, that's now changed into a minus. Okay. And then you would follow the same process. You would just integrate that one to get x over 2. And this one you would become sine x, sine 2x over 4. Okay, so that's that one. Again, if we needed to integrate, let's say, sine cubed x dx, then again, we would just think of this as being sine squared x times by sine. So I've just got a question there. Someone's wondering how long am I live and what am I going to cover? I think, to be honest, Felix, I'm going to do maybe round about an hour-ish. And I thought today I would concentrate just on integration, Felix. So in this live stream, I'm going to be going over integrating tricky things that aren't covered. Some of the things that I know maybe aren't covered by textbooks, and some of the things that I know where students go wrong. So at the moment, I'm doing sine squared, sine cubed. I'm going to do sine to the 4th in a minute. And then after I've done sine and cos to the 4th, I'm going to look at these 2 examples that you can see on the screen, which are tricky examples of like the chain rule backwards. Okay. And then after we've done that, I might look at an example of integration by parts that is really tricky, that is not on the not covered in a lot of textbooks, and very often isn't taught in a number of schools, but is something that you could be required to know for the exam. And then after that, I'm going to go through a few exam questions if there's any time remaining. So Felix, in answer to your question, I thought today I'd concentrate specifically on integration because of the fact that I know that that is, that's one of the things that a lot of my students ask me, can we do integration? Okay. So yeah, it's going to be all integration today. Okay, so you're so welcome, Felix, no problem. So now what we've got here is we're integrating sine cubed. Okay, so we've got sine, think of it as sine squared times sine, and then the sine squared, just like we did before, is going to be replaced by 1 minus cos squared x, okay, times by sine x. And then you expand the bracket, so you end up with sine x minus sine x times by cos squared x. Okay, and we integrate that dx. And then this one is fine. So sine integrates into minus cos. Okay. And then what we do is we integrate the cos squared. So we raise the power by 1, divide by the new power. So that goes to 1/3 cos cubed x. And we divide by the derivative of the inner function. And cos differentiates into minus sine. So we're going to divide by minus sine there, which means that that minus sine cancels out like that. So that cancels, and we end up with minus cos x plus 1/3 cos cubed x. Someone's asking, is it possible to go from a D to an A star? 100%. I see students every year going from a D to an A star. I have on rare occasions had students go from an E to an A star, believe it or not. But with more frequency, I have seen students going from a D to achieving A star. It is possible, but it would require quite a bit of work, and you'd really need to be like getting your head down and working hard, you know, from now until the exam. But it is possible, and it does happen. I do see it like pretty much every year. Okay, so I've done integrating cos squared. I've done integrating cos cubed. Let me just tell you about how you would integrate cos to the 4th. Okay. Now, this one, again, this is a super tricky one. So cos to the 4th, okay? So if we were required to integrate cos to the 4th dx, what you would do is you would think about it as cos squared x squared. Okay, so you imagine it's cos squared squared. And then, if you remember from earlier in this live stream, we said that cos squared can be replaced by a half add a half cos 2x. So what you do is, if you have to integrate cos to the 4th, you think of it as cos squared squared, and then you say, okay, cos squared is a half add a half cos 2x squared, like that. All right. And then what you do is you then basically expand that whole thing. Okay, so let's expand this bracket now. So that's going to give us a half times a half is going to be a quarter. And then we're going to have another quarter cos 2x and another quarter cos 2x. And then finally, we're going to have a quarter cos squared 2x. So all I've done in this stage is literally just expand that double bracket. Okay. Now we can collect our like terms. So we get a quarter, and a quarter add a quarter is 2/4, which is a half. So that goes to a half cos 2x plus a quarter cos squared 2x, okay, dx. So what we've done is we've said cos to the 4th is cos squared squared. Cos squared is a half add a half cos 2x. We expand our brackets, okay, and when you expand the brackets, we go from a quarter add a quarter add a quarter add a quarter. Those two we collect like terms, and that goes to 2/4, which is the same as a half. And now we're almost ready to integrate it. There's just one little problem, this, because we've got another cos squared again. So believe it or not, we need to use the idea that we've already used, but again. So what we do is we say cos squared, so I'll put the quarter there, and we say that cos squared is going to be a half plus a half, but this time it's cos 4x, okay? Because remember, when we replaced cos squared, it became double there. Look, it became 2x. So the x became 2x. So if we've got cos squared 2x, when we basically use the double angle formulae, that's going to become cos squared 4x there. So be careful about that one there. Okay. But now we should be good to go. Okay. So let's have a look and see what we've got. So here we go. Whoops, like that. So we're going to say now I can expand that bracket. So we've got a quarter add a half cos 2x plus that's going to become an eighth plus 1/8 cos 4x. And this is pretty straightforward to integrate this whole thing now. It's no problem at all. By the way, a quarter add an eighth is 3/8. So when we integrate that, that's going to become 3/8 x. So we've dealt with that and dealt with that one. This one, cos integrates to sine, and then we need to divide by the derivative of the inner function. So that's going to become sine of 2x and a quarter there. And then finally, cos integrates to sine, and we need to divide by 4. So that's going to go to 1 over 32 sine 4x add c. Okay, so that's our final answer, and that's how you would integrate. I've seen that kind of question. Well, some of the text, the Edexcel textbook indicates that that question would be worth 8 marks if it came up. And they say that there's 4 marks, first of all, for changing it from the cos to the power 4x into this format here that's ready to integrate, and then another 4 marks for doing the integration. So if anything like that came up in the exam, you know, it could potentially be worth as many as 8 marks. So that's how you would integrate cos to the 4th. And by the way, I won't go through the whole thing, but if you had to integrate sine to the power 4, what you would do is the same kind of process. You would think of it as being sine squared x squared. And then you would say sine squared using the double angle is a half minus a half cos 2x. So remember, it's the same as before, except instead of a plus, we've got a minus here. And it would be that squared. And then you would do exactly the same process that we did down here. You'd expand this whole thing. And then once you've expanded it, you'd be ready to integrate. Okay. All right, perfect. Now, I'm not going to go into too much detail on it, but I just thought it's interesting for you to see how you would go about integrating something like if you had to integrate cos to the power 5. So we've done squared, we've done cubed, we've done to the 4th, but what on earth would you do if you had to integrate cos to the power 5? Okay, I haven't seen this particularly covered in any textbooks, but it's useful to know what you would do. Well, you would think of it as cos squared x times by cos squared x times by cos x. Okay. Now, here's what we're going to do. So somebody's asked, do I recommend taking a factor out while doing the integration? Yeah, very often I do that, Grace. Like it can in various circumstances make life easier. Yeah, so I think a lot of the time, Grace, I would take a factor out when doing integration. Now with cos to the 5, I've thought of it as cos squared times cos dx, and cos squared is going to be 1 minus sine squared, okay, times by another 1 minus sine squared. So what I'm doing is replacing cos squared with 1 minus sine squared in both cases. Okay, I'm now going to expand this double bracket here. So that's going to go to 1, and it's going to go to minus 2 lots of sine squared x plus sine to the power 4x, all times by cos x dx, like that. Okay, so all I've done is literally broken it down into cos squared, cos squared, cos. Cos squared has become 1 minus sine squared. Cos squared has become 1 minus sine squared. Expand that double bracket. That gives you 1 minus 2 lots of sine squared x plus sine to the 4th. Now you expand your bracket. Okay, so that's going to give us cos x minus 2 lots of sine squared x cos x plus sine to the power 4x cos x. And this turns out to be really nice to integrate using the chain rule backwards. So cos is straightforward. That just goes into sine. This one, I think about my outer function is something squared. My inner is sine. So it's going to go to, it's going to go to sine x cubed. So I've raised the power by 1, divide by the new power, which is 3. And when I divide by the derivative of the inner function, the derivative of the inner function is just cos. So that cos cancels like that. Okay. And then over here, I'm going to raise the power by 1, divide by the new power. So that's going to become 1/5 sine to the power 5x. And then you divide by the derivative of the inner function, and the derivative of sine is cos. So the cos cancels. Okay. And that's our answer for how you would integrate sine to the power 5x. Okay. Again, if we wanted to integrate, how we'd integrate cos to the power 5x. If we wanted to integrate sine to the power 5x, we'd use the exact same process, by the way. Okay, so it would work out that you would basically think about it as sine squared times by sine squared times by sine, and then you would replace both of those sine squareds with 1 minus cos squareds. And you would expand your bracket, and then each one of those bits that you get would be accessible to the chain rule backwards, like what we've just done here. So I just thought that's a useful little thing to look at, just to, you know, how we would do that, just integrating some unusual things there. Now, I just want to now talk next about these two examples that I've put here on the left-hand side of the screen, okay? Because I know in my work with students, using the chain rule backwards is something that people get really, really confused about. And I think in particular, these ones are, I've taken these from an Edexcel textbook, and these two are pretty tricky, okay? And what's kind of like not very nice about integrating these two is the fact that we've got cos 2x over here in this denominator, but we've got just x's here. And that's the first kind of like red flag, as it were, yeah? Because you can't really sort of integrate something when you've got part of it in terms of 2x, and part of it is just in terms of x. Now, whenever you get sine x cos x written together as a product, that's a massive indicator that you might want to be considering using the double angle formulae for sine. Okay, so in other words, sine of 2x using the addition formulae here from the formula booklet is 2 lots of sine x cos x. So this is like our first step, as it were. So what we're going to do is, if you ever see sine x cos x, use this identity to deal with it, because what it means is a half of sine 2x is equal to sine x cos x. Okay, so the fact that we've got sine x cos x in the question, we can replace it with a half sine 2x. So let's do that as our first step. Okay, I'm going to put that up there at the top. It's going to be a half sine 2x, and I'm doing, by the way, this one over here at the top. So sine x cos x has been replaced by a half sine 2x, and our denominator is now cos of 2x plus 3, and I'm going to write that as to the power of a half, just because it makes it easy to deal with. Okay, now again, I know that this is an unusual method that you might not have seen for using the chain rule backwards, but I find it super helpful, and I think a lot of the students that I work with in my groups find it helpful as well. When I'm trying to use the chain rule backwards, I like to identify what's the outer function, what's the inner function, and what's the derivative. Now, in this case, my outer is something to the power of minus a half. So in the denominator here, we've got the power of a half. So it's something to the minus a half is my outer function. In that case, my inner function is my cos 2x add 3. So I'm going to write that there as cos 2x add 3. And then I say to myself, what is the derivative of my inner function? Well, cos is going to differentiate into minus sine. So that's going to go to minus sine 2x. And then using the chain rule, I would need to times by 2. So the derivative is minus 2 sine 2x. Okay, so I've identified my outer, my inner, and I've differentiated my inner. Now, the chain rule backwards is that we're going to integrate the outer, and we're going to divide by the derivative of the inner. So let's see how that applies to this question here. So when I integrate this, I'm going to raise the power by 1 and divide by the new power. So it's going to be something to the half, and I'm going to divide by a half. Okay, so I've raised the power by 1 and I've divided by the new power. Okay, so, and I've still got here a half sine 2x there in the numerator. And this now is cos 2x add 3 there. So integrated the outer, and now I'm going to divide by the derivative of the inner. Okay, and the derivative of the inner is minus 2 lots of sine 2x. Okay, so let's see what's going to happen. Some stuff's going to cancel out now. So that half is going to cancel with that one. That sine 2x is going to cancel with that one. And I'm going to get my answer here as minus a half, open brackets, cos 2x plus 3 all to the power of a half add c. And that's our answer done. Okay, so I just thought that's a really nice little method. Okay, identifying the outer, the inner, and the derivative as a way of integrating using the chain rule backwards. Now let's see how that same approach applies to the one underneath, sine x cos x, but this time the difference is here we haven't got a square root symbol in this second one. So we're trying to integrate in this one sine x cos x, okay, sine x cos x, and we're going to have cos 2x add 3. Now, Dorcas is asking, how do you know that you should not use a substitution for this one? And I think the answer is, like, sometimes you can use substitutions to integrate certain things. But I think in answer to your question, Dorcas, and I hope this makes sense, if you can see a pattern that you've got an outer, you've got an inner, and you've got something to do with the derivative of the inner, then that is an indicator of the fact that it's going to be the chain rule backwards. So I think really the best answer to your question is, if you can see that you've got an outer function, an inner function, and a derivative, then that's going to be the reverse chain rule. Okay, so that's how, those are the elements that I'm looking for. Now, just like before, this sine x cos x, exactly as in the same as in the previous example, is going to get replaced by a half sine 2x. So that's step one. Okay, so I'm going to replace that by a half sine 2x using the addition formula. This time it's a little bit different in our denominator. We've got cos 2x add 3, okay? And we're integrating that with respect to x. Now this time, my outer, I would think of as being 1 over something, okay? 1 over something is my outer. Again, my inner is my cos 2x add 3. And the derivative of the inner is cos differentiates again into minus sine 2x. But then we need to times by the derivative of the inner function, which is 2. Okay, so I end up with minus 2 sine 2x like that. Okay, perfect. Now we're going to integrate the outer. We're going to divide by the derivative of the inner. So let's do that. When I integrate 1 over something, that goes to ln. So it's going to go to ln the modulus of cos 2x add 3. Okay, like that. So I've integrated my outer. Remember, I've still got up here this sine 2x here. And then I'm now going to divide by the derivative of the inner. And the derivative of the inner is minus 2 sine 2x. So let's see what happens. So that sine 2x cancels with that sine 2x. And then a half divided by minus 2 is going to go to minus a quarter. So that's one going to give me minus a quarter ln mod of cos 2x add 3, like so, add c, and that's it done. Okay, good. Well, I'm glad that makes sense to you, Dorcas. I'm glad that makes sense. But I really like that little method, identifying the outer, the inner, and the derivative. And if on my YouTube channel, I've tried to like divide the whole syllabus into the chapters that follow the Pearson textbook, Pearson Edexcel textbook. So on my channel, you should be able to find the chapter that's just to do with integration. And on there, I think I've got quite a lot of examples of various types of integration, and you'll find ones like that. Okay, so that was the first thing I wanted to do. Now, the next thing I wanted to look at was a really tricky integration by parts. And it's an integration by parts question that is not covered in the textbooks, okay, that I'm aware of. And it's kind of like intriguing. So let's imagine we wanted to integrate, let's say we were going to integrate sine x e to the x by using integration by parts. Okay, so we want to integrate that one. Now, I personally like to use that little method when we're using integration by parts. We don't know which bit's going to be the u and which bit's going to be the v dashed. In fact, let's just have a look at our integration by parts formula from the formula booklet. There it is. So integration by parts is the integral of u v dashed is equal to u times v minus the integral of v u dashed. Okay, so that's our parts formula. And there's a little, I mean, I'm sure that a lot of teachers are familiar with this, but there's a little acronym we can use. And I know there's a further maths version, but I'm just going to go with the A-level version. The A-level version is you can be late. Okay, now L stands for logs. A stands for like algebra. I'll just write X for algebra. T stands for trig. And E stands for exponentials. Okay, And this is like the order of prioritization about what you would choose to be the u and what you would choose to be the v dashed. Okay. Yes, that's right. There's a further maths is ilate. Yeah, exactly. So the further maths version, someone's putting in comments, is ilate. The further maths version has little I at the start, and that's to do with inverse trig. Okay. But I'm just going through the regular maths version for now. So let's look at an example. Let's say, for example, I wanted to try and integrate. Let's say I had x cos x like that. Okay, and then let's say I had ln x times by sine x. And then let's say I had e to the x times by x squared. Okay, so basically, if I was going to try and integrate these ones, what I would do is in this first example here, I would say I have got algebra and I've got trig. Okay, so I would say the algebra is going to be the u, and I would say that the trig is going to be the v dashed. Okay, so that is how, in that example, I would decide which bit was going to be my u and which bit was going to be my v dashed. Okay, oops, my pen's failed there. Just let's go switch to a different pencil. So yeah, that would be the u and that would be the v dashed. And then in this next example, we've got logarithms and we've got trigonometry. Okay, so logs is the top priority for A level. So we'd say that that's going to be our u, and we would say that our sine is going to be our v dashed. And then in this last example, what have we got? Algebra and exponentials. Algebra is higher priority than exponentials. So that would be our u dashed, and that would be, sorry, that would be our u rather, and that would be our v dashed. And this one would probably require a double application of parts. Okay, so that's how it works. Now let's apply that method to this one. So what have we got? We have got trigonometry, okay, and we've got exponentials. So therefore, that's going to be our u, and that's going to be our v dashed. Okay, so we're saying that u is therefore sine x. So therefore, u dashed is going to be cos. We're saying that our v dashed is going to be e to the x. So therefore, our v is also going to be e to the x. So we've got everything we need now to like substitute into our formula for parts. So let's just do that. So we're saying here that the integral of sine x e to the x dx is equal to u times by v, which is going to be u is sine x times by v, which is e to the x. Oops, a bit heavy-handed there, pressing too hard on the pencils. There we go. So it's going to be sine x times e to the x. So that's our u times our v from the formula there, minus the integral of v u dashed. So v is e to the x, and our u dashed is going to be cos x. Okay, fine. Right, so this looks like it's going to be one of those ones where it's a double application of parts again now. Okay, so we need to now do parts again on this term here. Okay, so e to the x cos x. So let's do this one. So what we're going to say here, so it's trigonometry and we've got exponentials. So our u is going to be our cos and our v dashed is going to be our e to the x. So we're doing a second application of parts here. So we're going to say, therefore, u dashed, when we differentiate cos, is going to go to, cos is going to differentiate into minus sine. So that goes to minus sine x, like so. And then our v is, dashed is going to integrate. So v is going to be e to the x, like that. Okay, so now when we put that into our formula, we're going to have, let's put a minus there and a bracket around this whole thing. And let's just write uv minus the integral of v u dashed. Okay, so here we go. Now, here we go. So we're going to do u times by v. So our u is cos x. So we have cos x. V is e to the x. And then we have minus v u dashed. Okay, our u dashed is going to be minus sine x. So that goes to minus sine x there. And our v is e to the x. So we're just, this is our subbing in for our second application of parts here. Now let's see what happens. So we're going to say minus cos x there, e to the x. So far so good. Those two minuses come together to make a plus. So plus the integral of sine x e to the x, like that, dx. And then we can now remove that whole, well, let's just have a check here. So we've got a minus there, keep our brackets around that. So those two have come together to make a plus, so that's fine. And we've got a minus in front of this whole thing. So this is now minus cos x e to the x and a minus sine x e to the x dx. Okay, now this bit here carried on from before was just our sine x e to the x there. And then this bit was our question. This was our integral of sine x e to the x. Now, can anyone see what the issue is that we've got here? The issue that we've got here is, look at this. We've got sine x e to the x again. So we don't appear to have got anywhere. In fact, it looks like we've gone round in a loop. And then you say to yourself, well, what on earth am I going to do with this? Am I going to basically do another application of parts on this one? But that would get me back to cos. So it appears to be unfathomable. It looks as though we're locked into this loop of going round between sine and cos and sine and cos. But there is actually a really nice little trick, okay? And the really nice trick is what you do is notice that's a minus, and that is sine x e to the x dx. You literally take that whole thing and add it over to this side. So you end up with two lots of the integral of sine x e to the x dx is equal to sine x e to the x minus cos x e to the x add c. So it's kind of like a little trick. And the reason that I wanted to look at this particular example is because, to the best of my knowledge, the textbooks don't cover this, but there's no reason at all why you couldn't be asked to do this in the exam. It's not like beyond the scope of the syllabus that you could be asked to do this, okay? So now all we do to finish this question off is just divide by 2. So therefore, our answer is that our integral of sine x e to the x dx is equal to a half, and I can factorize out an e to the x, and we have sine x minus cos x plus c, like that. So there you go. That is our final answer. And by the way, that same approach would also work if you were integrating cos x e to the x. But I just thought that was a super useful. In this live stream, I've been wanting to look at a few sort of unusual little things that you know, a lot, in my experience, students are not particularly aware of. And that's one of them. You know, that's, I think, quite useful to know how to do that. And again, at the start of the live stream, we were looking at how to integrate cos squared, cos cubed, cos to the fourth, and cos to the fifth, and sine squared, sine cubed, sine to the fourth, and sine to the fifth. Okay, so that's a little bit of introduction there into a few sort of interesting things. Now, what I would like to do now is, I thought we'd have a look now, just a little bit of just some general kind of like integration questions. Okay, so let me just have a look at that. And I'm going to use, let me just see, I think I've downloaded it here. If I just quickly open it up. Okay, so go to downloads. Here we go. Yeah, integration. Here we go. So let's just look at some general integration questions here. Oops, bring our studio over here. There we go. Okay, so integration, and let's see where we're going to start. Where should we start? What's a good one? Actually, I know a good one to do. A good one to do I like, which I think is an interesting question to integrate, is, so we're looking at actual exam questions now. And by the way, this is a really good website. I don't know if you guys are aware of it, but it's super useful, called Yesterday's Maths Exam. So I know a lot of people are aware of the website Physics and Maths Tutor, but Yesterday's Maths Exam is a really good website where they've got lots of exam questions grouped by topic. So I definitely recommend that you perhaps think about that. I'll just show it you actually, just so you can see what I'm talking about. So if I just go to, this is I think it's a super useful resource for your revision. So it's called Yesterday's Maths Exam, just to show you what it looks like. There it is. And you go to, so for example, A-level. The reason I like it is if you go to A-level, click Edexcel and scroll down, then the person who's made this site has really nicely separated this into all of the topics, grouped by question. So at the moment, I'm looking here at the integration one, but you could pick anything. So let's say you pick parametrics. I mean, look at that one. I've been through that question on my channel, actually, I think. So if you want to look on my channel, you'll see that one. But what's really nice about this is the person who created this has like put all of the, for example, all these parametric questions together. And these are all past exam questions. So really nice, useful website. there. Definitely a big shout out to yesterday's maths exam. Now, what I would like us to do is I'd like us to just look at one of these questions. Let's look at, there's a really nice one, I think, that's worth quite a lot of marks. I think it's a bit higher up. So I scroll down and we just look at this one. Where is it going? It's one I like it because it's got x and ln x in, which is quite nice. Here it is. This is a nice question. So yeah, let's look at this one. I think this is quite interesting. So in this one, it says, so again, this is an exam question, and it says figure 2 shows a sketch of part of the curve with the equation y is equal to x ln x. Okay. And it says the line L is normal to C at the point P, which has got coordinates EE. The region R shown shaded in figure 2 is bound by the curve C, the line L, and the x-axis. Okay. Now show that the exact area of R is equal to A E squared plus B, where A and B are rational numbers to be found. Okay. So somebody here saying that they're from India. Can you please tell me which grade this chapter integration belongs? I think, to be fair, in answer to your question, integration is very often like grade A and A star. It's one of those topics where they do like to kind of like put these tougher integration questions near the end of a paper. So I'd say you could think of it as being kind of like grade A or A star to be in answer to your question there. Right, let's look at this one. So how on earth are we going to tackle this? So we've got to try and find that area R. Well, I think that one of the first things that we need to do is to like separate this curve into a couple of little separate bits. Okay. So here we go. There is our curve. Now I'm going to draw a line coming down here from P. So we've got E and we've got E here like that. So we know that that is E. Now, if we can basically find the area of that and find the area of that triangle, I think that's going to be the way that we need to approach it. So let's first of all, I'm going to call those areas A and B just for the sake of argument. So we're going to try and find this area that I've labeled A. This is going to come from integrating the curve in between here and E. Okay. The only question is, how on earth do we work that out to start off with? Well, let's have a think about that. So the equation is y is equal to x ln x. Okay. So we're going to start off by saying this curve is going to cut the x-axis when y is 0. So we're going to say 0 is equal to x ln x, which gives us two solutions. One of them is going to be x equals 0, and the other is ln x equals 0. Okay, so now when we reverse our logs, this is going to go to x is equal to e to the 0, so therefore x is equal to 1. Okay, I'm still pressing down very heavy-handed, keep breaking these leads. Okay, so that is 1 there. Okay, because we reverse the logs, so we get x is equal to e to the 0, and e to the 0 is 1. So we've established that we're going to integrate x e to the x, so x ln x, in between 1 and e. So that's our step 1. So we're going to integrate between 1 and e the equation x ln x. Now, this one is going to be an integration by parts. So let's write down our little thing. You can be late. Okay. And what have we got? We've got logarithms and algebra. Logs is top priority. So that's going to be our u, and that's going to be our v dashed. Okay. Let's write down the formula. So the integral of uv dashed is equal to uv minus the integral of vu dashed, like that. Okay, so let's write down our u dashed and our v then. So we've got that u is ln x. So therefore our u dashed is going to be 1 over x. That's a u there. Our v dashed is going to be x. So when we integrate that, that's going to go to x squared over 2. So we've differentiated the u and we've integrated the one that we've called v dashed. So we're now ready to sum into our formula. So the integral of x ln x is going to be u times by v, which is going to be, that's a v there, not a v dashed. So we're going to do u times v. So that's going to go to x squared. Okay, what's going on here? Gosh, we're having a pencil meltdown here. So that's going to go to x squared over 2. That's u times by, that's our v rather, times by our u. Okay, so there's u times v. And then that is going to be, is A for the shaded area? Yes. So basically what I'm working on here now is for this bit up here at the left that I've called A. So I've divided the shaded area into two bits. I've called it A and B. And this using integration by parts is helping me find out this little area that I've called A. We're going to come to that bit in a minute, okay? So let's have a look. So we've got x ln x is equal to u times v minus the integral of v u dashed. So our v is x squared over 2, and our u dashed is 1 over x, like so. So that is going to, squared is going to cancel with the x, so that is just x over 2. So when we integrate that, that's going to go to raise the power by 1 and divide by the new power. That's going to go to x squared over 4, like that. Okay, that's fine. So what we've got is x ln x minus, oh no, so that's our question. So the integral is going to be x squared over 2 times by ln x minus x squared over 4, and we're evaluating that whole thing between e and 1. Okay, all right, that's fine. So let's do that. I'm just going to check that that's looking good. So we've got x squared ln x over 2, yep, and the other bit is going to be x squared over 4. So everything's looking good there. So now we've just got to put our limits into that and see what we get. Let's have a look. Okay, so here we go. Let's substitute e into this. So this is going to go to e squared over 2 and ln of e minus e squared over 4, okay, minus, open bracket, 1 squared over 2 times ln of 1 minus 1 squared over 4. Okay, ln of e is 1, so that is just going to be e squared over 2. Then we're going to have minus e squared over 4. Ln of 1 is 0, so it's going to be minus 0. And then we're going to have plus a quarter, because a minus and a minus will make that into a plus. Okay, so therefore we've got e squared over 2 minus e squared over 4, which is a half take away a quarter. So that is going to be e squared over 4 plus 1/4. Okay, so that's the first thing we've done there. Okay, we've got e squared over 4 plus a quarter. And that is the answer to the area for that first little bit there. Now, let's see what's next. Now, we need to find the area of this triangle that I've called B. And in order to do that, what do we need to know? We really need to know where this line crosses the x-axis. And in order to know that, we need to know the equation of this line. Okay. Now, there's two things we need to know to get the equation of a line. We need to have a point, and we need to have a gradient. And in order to get a gradient, we're going to need to differentiate the x ln x, okay? Which is why I wanted to look at this question, because it's nice, because we're having to integrate x ln x and differentiate it. So the first thing we're going to do now is we need to find if y is equal to x ln x, we need to find an expression now for dy by dx, okay? And this is going to be the product rule. So I'm going to call that one u and that one v. And the product rule is going to be u dashed v add u v dash, like that. So when I differentiate my u, it's going to go to 1. So that is going to go to 1 times by ln x. And then when I have my u, that is going to be x. And when I differentiate my v, that's going to go to 1 over x. So when I differentiate this expression, it's going to go to ln x add 1, like that. Now, so far, so good. I found an expression for my gradient, okay? But what I need to do now is I need to find out what is the gradient at the point where the x-coordinate is e. So at the point where the x-coordinate is e, we have got ln of e plus 1. Ln of e is 1, so we have 1 plus 1, so we have 2. So our gradient of our tangent at the point P, so the gradient of the tangent at the point P is 2. So now we've got everything we need to find the equation of this line. So the equation of L is going to be given by y minus y1 is equal to m x minus x1. Okay, so y minus e, because that's our y, is equal to our gradient. Now I've got to be careful, because it's the gradient of the normal. and the gradient of the normal is going to be negative the reciprocal of the gradient of the tangent. So therefore our gradient of our normal is going to be minus a half. So that is going to be minus a half there, and we're going to have x minus x, which is going to be the x coordinate is e. So this is looking good now. So y minus e is equal to minus a half x plus e. And then I'm going to say that y is equal to minus a half x plus 2e, because we add that e over to this side here like that. So that's our equation of our line. So now what we need to say to ourselves is, what is this going to be when the y coordinate is equal to 0? Okay, so let's think about that. When the y coordinate is going to equal 0. So when the y coordinate is equal to 0 in this equation, we're going to have 0 is equal to minus a half x plus 2e, like that. And then we're going to take this over to the other side. So we're going to have a half, or let's just be careful. Let's be super careful. Now I can see that. Let's have a look. When I've expanded this bracket here, that should be minus a half x, and that should have been plus a half e. There we go. Because when you do that one times that one and that one times that one, we get minus a half x and we get plus a half e. That looks a lot better. Okay. So there we go. So that's fine. And then this is so that there is going to be, that's a half e. So let's just double check that. So it's minus a half, and that is e. So that is going to go to a half e like that. That should be a half e. Now I add the e over to the other side, which is going to give me 3 over 2. So a half add 1 is going to give me 3 over 2. So this is 3 over 2e like that. Okay, that's fine. Now let's think about this. When y is equal to 0, we're going to basically add this x over to the other side. So we're going to have a half x is equal to 3 over 2e. And if I times everything here now by 2, I get that x is equal to 3e. So 3e is equal to where we cut the x-axis on that curve. Okay, so basically we found that this here is 3e. So now we're in a perfect position to find the area of this triangle B. Area is just a half base times height, and the base is going to be 3e, take away e, so in other words 2e. The height is e, because that's the y coordinate there. So that ends up as just being e squared is the area of the triangle. And now we're almost there for finishing off this question, because we're just going to bring our two answers together now. Okay, so we found out that the area of B is e squared, if you just remember that. And here was our area of A. So therefore the area of what I called A and the area of what I called B, that was e squared. So I'm going to add this together. So e squared over 4 add e squared is going to be 5 over 4 e squared. And then it is plus 1/4, which is our answer. Now let's look at the question and see what the question says. The question says, show that the exact area of R is equal to A times e squared add B, where A and B are rational numbers to be found. So the A from this question is the 5 over 4. So there's the 5 over 4. And the B is the quarter. And that's the question done. Okay, there we go. Perfect. Well, I hope that you all found that helpful. I just wanted to do that, just like a little, give you a sort of overview of a bit of integration, because I know that that's one of those topics that students find really, really difficult. As I say, if you have a look across at my channel, I've been trying to be, in the creation of my channel, try to be really meticulous in kind of like breaking it down and indexing it all by topic. Yeah. So if you're in year 12 or year 13, then you can find that I've done playlists for each individual chapter, which I think you would find really helpful. So you just go to my YouTube channel, click on the chapter, and you can see there's a whole playlist there of all the questions by topic. I've also done a number of past papers. So there's a few sort of like older papers on there that you could have a look at as well. You might find it useful to maybe try a paper as you work through the questions as well. And of course, I've got my groups as well, which, you know, you can click on the link in my channel description if you want to find out more information about how you could join me in one of my small groups, and you'd be very welcome to do that. In fact, I would highly recommend that in the run up to the exams as well. I think that you could find that quite useful. Okay, well, thanks so much for watching, everyone. I hope you found that helpful, and I'll hopefully see you all again soon. Thanks, everyone.